Hi, this is Mr. A with another video in the How to Science Fair series. This one's going to focus on the experiment. The experiment is sort of the classical scientific method approach to learning about something that a lot of people think of when they think of science fair projects. Now, also, just as a disclaimer, again, while I do have a lot of experience with science fairs, they're all sort of focused on the district where I teach. And you want to make sure you check with your local school district rules and regulations before you go too far down any one path. Again, science is science, but everybody runs their science fairs a little bit differently. And while I'm confident this information is going to be useful to you, whatever district you're in, again, it always pays to check first to make sure you're doing what they're looking for as well. All right, so if you're watching this video, you probably are thinking about maybe trying to do an experiment for the science fair. And experiments try to get you to think about how a scientist tries to approach a problem. A scientist's job is to try to figure out sort of the rules of the game. How do things happen in nature? And the way they do this is they ask a question, and then they create an experiment to help them answer that question. So it's kind of like you're a detective and you're trying to figure out how a very, very, very small slice of the world works through your investigations. Now, a good experiment can look a lot of different ways. At your level, starting off in a science fair, it's probably going to contain these 5 elements if you want to make sure you're doing everything you should be. Number 1, you want to make sure that you ask a good question. Number 2, you want to set up a good procedure. Number 3, you're going to collect the data. Number 4, you're going to present the data, sharing what you found. And then you want to wrap up your investigation. We'll go through each of these step by step to make sure you have a sense of what you should be doing. Asking you a good question. Again, we talked a little bit in the last video about how to pick a good topic in general. That's not what this particular discussion is going to be about, but you want to make sure you've picked a topic that you're going to be interested in studying. That's a good place to start. But once you've picked a topic that you're interested in, you want to make sure that you sort of narrow down the question you're going to be trying to investigate. One of the main challenges I see new science fair participants encounter is that they don't phrase their question very carefully. And if you don't start off with a good question, it's sometimes kind of hard to get good answers as a result of it. And really, the main idea is you want to focus on changing one particular thing. And then you want to see how that one particular thing may or may not influence something else in particular. You change one thing, you see how it affects something else. And that's the best way to get clear results from your investigation. The thing that you're changing, if you want to use sciencey words, is the independent variable. We call that independent because you are controlling the value independently of everything else. And it's called a variable because a variable literally means something that's able to vary, something that's able to change. So the independent variable is something that can change, but it's something that you are choosing the value of each run. And it varies because you're going to probably run the experiment multiple times. And then each time you're going to change that independent variable by just a little amount and try to see how that influences the results that you get. Now, the results that you get are going to be called the dependent variable. The dependent variable, dependent means what you get depends on the independent variable. Now, between you and me, it may not actually depend. There might be no effect whatsoever, but we call it the dependent variable because we're looking to see if there is some sort of dependence. And again, it's called a variable because in an ideal world, it will change as a result of what you're doing. Now, examples of that throughout the presentation, we'll focus on 2 different sort of hypothetical experiments. The first hypothetical experiment is going to be based on the idea of working with seeds. And just as a little behind the scenes, this is based not loosely at all after an experiment that I did when I was a kid in science fair. And I'll give you some insight as to how it turned out a little bit later. All right, so how does changing the amount of light that seedlings get impact the size of the vegetable? That's going to be the question we want to try to answer here. Again, the first thing that we want to ask is what's the independent variable here? The independent variable is the amount of light you let the seedlings get. How much light do they get each day? you're going to control that. The dependent variable, we're going to see, I mean, there's lots of different ways to impact how light impacts growth. In this particular experiment, we're just going to get the vegetables and we're going to mass them. And then we will imply from the mass of the vegetables how successfully the light was in helping them to grow. But even right there, you can start to make decisions. How you evaluate the success of your experiment. Two kids might start off with the same question, but might evaluate it in different ways. And that's okay in science. The other hypothetical experiment that we're going to be working with is, let's say, birds. And sometimes in an experiment, you're not actually controlling everything, but you're watching something that's already happening and trying to understand it in the context of something else that might be changing. So here, like I don't have control over birds. I mean, birds are going to do what birds are going to do. But let's say, hey, I'm wondering if the temperature outside influences how many birds visit a feeder that I have in my backyard. Again, I can't control the temperature. I can't control the number of birds, but I can look at the temperature every day and see whether or not there might be a connection between the temperature and the number of birds that visit each day. Now, there's a phrase in science that says correlation is not causation. That's just a fancy way of saying just because there's a connection doesn't mean it's being caused by what you think it is, but at least it's a start to sort of see, hey, what might be going on. So in this case, we're going to treat the independent variable as the temperature outside. Now, again, I'm not actually controlling the temperature, but I'm going to watch how the temperature changes and record that every day. And then I'm going to see every day, maybe I'll take a video of the bird feeder, and then I'll just watch it at 2 times speed or something like that in the evening, and I'll just see how many birds visited the feeder during that hour. Okay, and again, there's lots of different ways to try to decide how many birds visit a feeder. You could test maybe how much bird seed's gone each day, or again, lots of different ways that you can design your experiment. We're just going to do it this way for our hypothetical experiment. All right, so once you have a good question, you want to make sure you set up a good procedure. A good procedure can help make it clearer the kind of results that you get from your experiment. And one of the big things when you're setting up an experiment is you want to try to keep as much the same as you can between the different measurements you take, because everything that you change could potentially influence the results that you get. And we're trying to be very, very focused on the one change you're focusing on so we can see how that influences your data. So we call this in science constants. Constants are things that maybe could change, but we don't allow them to, because we only want to change one particular thing. When you're setting up your procedure, the IV refers to the independent variable. Ideally, try to change the independent variable by the same amount each time if you can. That just makes it easier to record and present your data later on. It's not vital, but it's just a nice habit to get into. When possible, it's nice to know what happens without any experiment at all. We call this a control group. The idea being, do we know what we would normally expect to see under just regular circumstances? And then what we can do is we can compare our results to what we normally would expect to see. And that gives us a little more context for understanding what actually happened. And finally, it's a good idea to think about what do you think might happen? We call this a hypothesis, an educated guess or a testable prediction about what you think might occur. Now, this could be informed by other knowledge that you have. And you can explain a little bit about why you think it's going to happen that way. But it's just a guess. When you're a older scientist, your hypothesis plays a bigger role in your analysis. But for now, you're just trying to think, hey, this might happen. All right, so let's see how this might go. If we're looking at the seed example, we're looking at how the seeds grow with regards to changing the light over time. As far as the constants go, we're going to want to make sure we keep the same conditions as much as possible between all the seeds. It means we want to use the same type of seed. We shouldn't be using beans for one part and peas for the other part. You want to plant them in the same soil. You want to water them the same. You want to keep the temperature the same. You want to keep everything as same as possible except for the lighting. When I was a kid, the way I did this is I set it up in my laundry room, and the light that I provided was actually through an electronic grow light. And then I was able to keep everything else really, really similar because they all were under the exact same circumstances. The only thing I changed is how much light each sample got when I turned the light on. And a good habit for this experiment would be to also grow a normal set of seedlings, exact same circumstances, but just maybe under regular circumstances. Maybe get a set of plants and maybe grow them, maybe in the living room or somewhere else that's got nice, normal, ordinary lighting, and see how they do. I will say that I did not do that during my experiment when I was a kid. All I did was have all these plants set up in my laundry room, and we'll talk about whether or not that ended up being a good idea a little bit later. All right, as far as the birds go, this is just, again, I didn't do this as a kid, but it could be a good project if you want to try it. So again, this is going to be comparing how air temperature influences how many birds visit your feeder. And again, it's nature, so you only have so much control over it, but try to keep as much as you can the same. For example, don't be switching out different brands of bird food every day. Don't change the location of the feeder. Don't change the type of the feeder. Don't position it in different parts of the yard. Try to keep the hour that you're looking at it the same. If you run the video, the hour you get home from school, maybe from, 3:30 to 4:30, try to run it from 3:30 to 4:30 every day. Don't run it in the morning one day, in the afternoon the next day. So even when you're watching nature, you can still try to make sure you're keeping things as constant as you can. And obviously you can't control the temperature of the air. You can't dial it in every day. But what we can do is we can record it every day. So when you're looking at your video each night, note what the temperature was that day and write that down too, so you can keep those connected with each other. All right, so in terms of collecting your data, stage 3, usually this isn't too crazy. It helps if you're organized though. When collecting data, the general rule is more data is better. 3 runs is okay. 1 run, it's kind of hard to tell what actually happened because you're not really changing your variable at all. 3 runs is better. 5 runs is better. 7 runs is better than that. As much data as you can for your time and circumstances is going to be better to try to get some results. And you want to think about how you're going to measure your data, and you want to make sure you collect it the same way every time. For the example with my seedlings project, measuring the mass of the seeds or the vegetables at the end of the time is a real simple way to measure how that change occurred. If I started off by saying, maybe I want to measure the plant height instead, that's a different way to do it. But however you want to do it, you want to make sure you're consistent the whole way through. So you want to think about it before you start. When you're collecting data, there is what's called quantitative and qualitative data. Quantitative data is numerical, measuring with rulers or electronic balances or graduated cylinders and getting actual measurements that are numbers and units together. But also it's useful to note qualitative data as well. Maybe with the bird feeder example, not just the number of birds, but maybe you can take a look if there's certain types of birds while you're at it. Also, record your data neatly and try to record it in the same place every day so you know where to find it when it's done. Maybe set up a table or put it in a computer spreadsheet so that you always can find it. So, for example, I already sort of previewed this a little bit. Let's take a look back at the bird feeder example, where you're changing the light and you're seeing how I just noticed I have the word seeds, but then birds eat seeds as well. So maybe that's a little bit confusing, but we'll say the seeds are the ones that are in the basement. So with seedlings and light exposure, basically what you're going to do is you're going to record which collections of plants are getting which amounts of light. And that's probably a little bit easier because once you have it set up, you probably don't need to record that every day. You're just going to turn it on and turn it off, and that's fine. So as far as this particular experiment goes, the way we're setting it up right now, we're just looking at the mass of the vegetables when we're done. there's really not a heck of a lot to do every day. You might just take plants. If you want to note the growth of the plants, the height of the plants, that's fine. But realistically speaking, we're just looking at the mass of the vegetables. So we just have to collect data when we're done. The birds, when you set up to collect your data, and again, there's lots of different ways that you could do this, but probably the easiest way is, again, just have a camera set up, turn it on for an hour, and then watch the video afterwards. The great thing about this is you don't have to be stuck for an hour outside watching birds. You've got your video, you can watch it inside at your comfort, you can watch it at 2 times speed, and you can get the data super easily. And if you had any questions about it, you've got all the data there on your camera. So you can just go back any day you want to and just review the data if there's other things you wanted to look at more closely. Once you've collected your data, and again, more data is better, you want to present your data. A good place to start with that is to draw a graph. Not all data corresponds to a graph well, but a lot of data does. And a graph is a great way to sort of present your data visually so people can get a sense of what's going on pretty quickly. And if you have questions about how to graph your data, this is a good time to talk to your science teacher about it, or your math teacher. Probably either one of them would be more than happy to take a look at your data and give you some advice on how you could present the data in a graph or two. The general practice for this is, when you're deciding what to put on your graph, the independent variable, what you changed, goes on the lower axis. We call that the x-axis, the horizontal axis. And then what changed as a result of it is the dependent variable. That goes on the vertical axis. And you plot the data and you see whether or not there's a pattern. So an example of how this might look in practice, I'm a little bit in the way, I apologize. So here is a set of data. There's 2 sets of data. Let's focus on the top set of data to begin with. And maybe we take the plants out of the ground at the end of our trial, however long we let them grow, 6 weeks or whatever. And you can see that I set up on the axis, is my finger going to show? All right, so in any case, the idea is that the light is what I controlled. That's the independent variable. So that goes on what's called the x-axis. That's the horizontal. I can't directly control the mass of vegetables, but it might be influenced, and that goes on the y-axis, the vertical axis. And this is just fake data. But you can see here, if you look at the grid of data, it's maybe a little harder to see what happens. But if you look at the graph, you can say, hey, when the seedlings that got 0 light at all didn't grow at all. The seedlings that got 4 hours of light grew some, and then 8 hours grew more, and 12 hours grew more than that. So you can see there's a trend kind of going upwards as you get more light. And that's an ideal situation. That's what you would like to see. When you look at your data, you want to see some sort of trend, some sort of connection between that. Now, this is fake data for a fake experiment. The bottom set of data is probably more like what I actually got when I was a kid. Let's take a look here. This is what I found when I did I think I was growing turnips, and it was an abject failure. None of the turnips barely grew at all, and there really wasn't any pattern. If you can see, between 4 hours and 12 hours, none of them grew well at all in those conditions. So the issue here is that my problem with my experiment is that I didn't have what's called a control group, meaning that I didn't have a set of plants growing under just sort of regular conditions. If I'd had a second, a different set of plants, maybe up in the kitchen somewhere, just growing with light from a windowsill or something, and they didn't grow at all either, maybe I could say, well, maybe it was a bad set of seeds or something like that. But by not having anything else to compare it to, I don't really know why. I'll never know why my turnips didn't grow. But they didn't. And but I still, I wrote up the data, completed the science fair project, and still got credit for it, and still did fine, because sometimes you're not going to get the results you think you're going to get. The other scenario we're talking about is birds. So maybe we go through and we plot the data. This graph's a little more complicated because your air temperature is going to change. You're not going to have a day 1, day 2, day 3, day 4 kind of thing, because some days it's going to be hot, some days it's going to be cold. So maybe in a hypothetical situation, we take a look at this data, we plot it out. And again, your math or science teacher can help you with this if it's a little harder for you. And we actually have a pretty good trend in the data. You can see there's a little bit of a trend where it kind of looks like the colder the weather is, we tend to get more birds than when it's warmer. So that would be something you could draw a conclusion from. Now, it is entirely possible you're going to plot your data and you're going to see something like this instead. Now, this setup, there's no really rhyme or reason to connecting the number of birds that visit the feeder and the temperature. It's all over the place all the time. And this could entirely be what you end up with when you look at your data. And that doesn't mean your experiment was bad. You just discovered that there doesn't seem to be a pattern there. And that is useful too. Knowing that something isn't there sometimes is as helpful as knowing that something is there. All right. Now, what some kids forget to do, they get their data and they think they're done, but you want to wrap up your investigation. If you watch any sort of detective show on television or something like that, usually there's that scene where the detective comes in and they explain, he or she talks about all the clues and just decides, hey, this is how I figured out the right answer. So we should do the same thing to wrap up our investigations as well. The gentleman above me up there is Enrico Fermi. He was quite the experimentalist back in the day. And he had a pretty famous quote. And he said, hey, when you're done with a scientific experiment, there's 2 possible outcomes. If the results confirm your hypothesis, your guess, then you've made a measurement. If the result is contrary to the hypothesis, he's saying if you don't get the results you think you're going to get, then you've made a discovery. So he puts it in a really great way to say, hey, if you don't get what you think you're going to get, that just means that you found out something that you didn't think you were going to. And that's a really exciting thing to happen in science. And when you look at your data, you want to say, you want to try to explain the results that you got. Explaining what you got is called a theory. I sometimes refer to that as the most logical explanation. You're going to take a look at your data and you're going to try to figure out, okay, why do I think the data worked out the way that it does? If it matches what you thought to begin with, that might be a little bit easier because you say, you know what, it sort of happened the way I thought it was going to happen. And this confirms my hypothesis. So my original understanding looks like it is on the right track. If it doesn't work out, this is perhaps the more interesting thing, because then you can stop and think about, okay, what was I maybe wrong about? What might be a different explanation for what's going on here than I thought initially? And it's kind of fun to be challenged to rethink about the data in that way. And I like to ask students to also wrap up their investigations with these 2 questions as well, the what ifs. If you could do the experiment again, what would you do differently? If you wrapped up the experiment and knowing what you know about how the experiment worked, would you do things differently? What would you change? Usually by the time you're done, you look back and say, yeah, you know what, I probably should have done this differently. And that's totally okay. That doesn't make your project any weaker. It just shows that you're thinking good science thoughts. And then also, if you could keep going, what would you want to learn more about? In science, when somebody presents their information to other scientists, that often acts as a springboard, or a trampoline for other people to jump on and go further with. So you might ask yourself, hey, what might be next if somebody was to look at this and keep going on? When I was a kid, I might take a look and say, hey, maybe what kind of plants don't grow well under artificial lights, because it seemed like my turnips did not grow well under a grow light. Maybe investigating further, maybe you're looking at the data and you start to see that maybe certain birds don't come every day. Maybe maybe cardinals come every 3 days or something like that. So maybe looking at your data, you might discover a new pattern and be like, hey, I wonder if certain birds come every day and certain birds come like every other day and things like that. What's the pattern in which birds come to the feeder? So the more information you get, sometimes the more questions that you find you can answer. So let's review real quick. So when we do an experiment, you want to ask a good question to start. And that's defined by a couple sciencey things like independent and dependent variables. You want to set up a good procedure. That includes things like making sure you try to keep everything as similar as you can, except the one thing you're changing. Those are constants. Maybe setting up a control group to give you something to look at to compare your results to. You want to collect the data in a careful, methodical way, saving in a place where it's going to be easy to find, where you can keep it organized. You want to present the data to your audience, probably with a graph if your data works out that way. And then you want to wrap up the investigation. You want to take a step back and think to yourself, okay, what did I learn? And what might I still have questions about? And that's the recipe for a good experiment. And I want to thank you for taking the time to watch this video about how to complete a good science fair experiment. There's a lot more to it than I talked about in this lesson, but this should give you the basics to get started in your own scientific explorations.